So, can we start?
Okay, let's start.
So, hi, nice to see you again. So, my name is Eden, as you may remember, and I haven't graduated yet, but give me like a week, maybe a week and a half. So, our second, so we're starting our second class about EEG, and today we're going to talk about mostly about spectral analysis and then a bit about EEG artifacts. Okay, so let's get into it. Yeah, so what is spectral analysis or spectral decomposition? So who here has learned about the Fourier transform? This is everybody, right? Almost everybody, okay. Well, it's still safe to assume to act like you haven't, because I learned about the Fourier transform when I was doing my military training when I was like 18, and I've been working with it ever since, and I still don't feel like I completely figured it out. So it's a very unintuitive idea. So I'm going to try to, even though you probably know a few things about it and you've read the paper, I'm going to try to give you a bit more maybe intuition about what it is that we're doing. So the idea is that every time domain function can be transformed and represented as a sum of basis functions. And in the case that we're talking about, these basis functions are sine and cosine functions. And this can be done for any function. It doesn't matter what it is. So basically, the idea of this transformation is that if we have, and I'm not going to get into math at all during this class, just more like maybe more intuitive hand wave your explanation. So if we have this function, the function of time, we can think of it as a sum of what's the name of the this function, Punctet Helem, Dirac.
Delta function?
What? Sorry? Delta function. Thank you. Yeah, that's what I was. So the sum of delta functions. So we have this function, which is this value here and 0 everywhere else, and then we have this function, which is this value here and 0 everywhere else. And basically, we can just construct a vector. So if we have like 1,000 time points here, this is a vector across in a 1,000-dimension space, where each time point has a coefficient that says what is the coefficient of this delta function, each of these 1,000 delta functions. And when we're doing the Fourier transform, what we're doing is basically taking this representation and transforming the space so that each axis of this space represents the coefficient of a sine function. Okay, this is the idea. So it's important to understand that this is not. It's not like we're taking a function and approximating it, getting as close as we can get with a sum of sine waves. This is a transformation, so no information is lost. We can go back and forth. It's just the way we turn the space. I said I'm going to go just a little bit into the math. So I said sine waves and cosine waves. So if you have 1,000 points here, 1,000 coefficients of these delta functions, then when we move to the Fourier representation, we actually have so half of that, so 500 or n minus n divided by 2 coefficients, but each one of them is complex. So we have one. So we have the same number of data points, but now we have 500 coefficients, each one of them having one value for the cosine and one for the sine wave. Or another way to think about it is that one of them would be the amplitude of the sine wave, and the other one would be the phase. So if we have this is going to make more sense in a minute. know what? Let's just move right ahead to the demonstration. So what I found that helps, if you have only a theoretical familiarity with this idea, it helps to look at what it actually looks like. So so we have these series of coefficients for sines and cosines. So if we increase one of them, we get a sine wave, and then if we increase the coefficient for the cosine wave of the same frequency, we actually change. So when we change the amplitude, which is the so yes, so I do need to draw this. So if we have a complex number representation, so this is 0, and we have our sine wave and cosine wave, or the other way, coefficient, then the amplitude of the resulting sine wave of the resulting oscillation would be the size of this vector, and the phase would be the angle of this vector. Okay, so by changing the ratio between the sine and cosine wave, we're actually, it's the same as changing the phase and the amplitude of this oscillation. So we can just, so another way to look at it is just move to a amplitude and phase, magnitude and phase representation, which is easier. So here we change the magnitude here and the phase here. All right, so now, for example, we know that every function can be constructed as the sum of these sine waves. So, for example, let's say we want to look at something, to have something which is completely different from sine wave, which is a square wave. So how does that work? So, I like this example of just showing how we can construct a function. So that if we start with, why is it not working? Okay, with a sine wave now. So this is now closer to a square wave, but it's not there yet. So we can say that we need to change the shape. So if we have like a 1 cycle per whatever this is per second wave here, we need to add a 3 cycle per second wave to make it look more like this. Wait, this is not right. Why is it not? Let's go back to this representation. All right, to make it look more like this. All right, and then we need to fix the error that we still have. So we add a faster frequency to make it look like this, and then etc. And eventually we get a square wave. Okay, so whatever you want to build with sine and cosine waves, you can. And now you would say, okay, but this is not really a square wave because you have all these squiggles here. It's not the same thing. So the answer is that, yeah, you're right, but the thing is, this square function, this square wave, it has, since we're talking about a discrete signal, that is, it has like a sampling frequency, then the question is, what is happening? So, sorry, I'll go back and say it clearly. When we say that we can represent any function in the world with sines and cosine waves, then, and all this is true also for continuous functions, but it's a different story. So it's easier to understand this with discrete functions. Sorry, it's it's a bit more complex in my mind than I expected. But okay, the idea is that we can represent any function with sine and cosine waves as long as that function doesn't have higher frequencies than what we can represent with the number of components that we have. So, for example, so are you familiar with the Nyquist law, Nyquist theorem? Anyone not familiar with it? Great. Okay. So the Nyquist theorem says that given a sampling rate of a signal, a discrete signal that is sampled n times per second, the highest frequency that can be represented, that can be contained in that signal, is n minus 2. And why this can be demonstrated pretty easily. So if we have a function that is sampled at this rate, right, then we can represent, so this is maybe 1,000 times per second, for example. So an oscillation which would be 500 cycles per second would look like this. All right. So if we sample these points, we can represent an oscillation that with a 500 cycles per second frequency. But something that oscillates faster, like this, simply cannot be represented by sampling 1,000 times per second, right? Because we need these data points. Okay. So so when we say that we can represent, was there a question? Yes.
So n divided.
Yes, because so if you want to represent an oscillation, then you have to have one data point here and one data point here, right? So it's 2 data points per cycle. Okay, this is really hand wavy, but I think this is the best intuition for this idea. So if you want to represent higher frequencies, you have to have a better sampling rate, and then you can see whatever is happening here. Okay, so while it's true that we're not really representing a true square wave here because there's all these squiggles, then the square wave wasn't really square to begin with because it was actually also sampled. It wasn't sampled with infinite resolution, right? It was sampled these time points. So it looked like this. But we don't know, so if we sampled here, and this is our function, right? We're just assuming that between those data points there's a straight line, but the information is not really there, we're just imagining it. So this representation is not really more accurate than this representation, right? So in a sense, yeah, this is a square wave, and we haven't lost or changed any information. We just changed the representation to a representation where instead of connecting the lines with straight lines, we're connecting them with the squiggles. But it's the same thing. All right. Yeah, that's pretty much it. Yeah, we can play with the phase, and we can mess up the signal. All right. Yeah, just by the way, just notice what happened here. So we took this really nice square wave. Where is it? Square. And we took one of the small high frequency phase values and we changed it. And all of a sudden we got this. Oh wait, no, this is not the phase. Sorry. Yeah. So we took one of these values and we changed the phase, and suddenly we get this oscillation where it wasn't there before, right? And this is because the phase really matters. If you want to construct a signal, you have to construct a function. All of the signs, it's not enough that the sine waves are there. They have to be in the precise wave with a precise phase so that they interact together to create the shape that you want. So we're going to talk about later more about the importance of phase and amplitude in EEG analysis. Any questions about this? All right. So we can, when you get the presentation, you can play around with this yourself. I think it's a, well, I wouldn't say it's a fun game, but you should try it. All right. Okay, so so this is just a quick introduction about Fourier analysis. So back to EEG. So why do we do frequency analysis? One reason is that we talked about ERP analysis last time, and as you remember, ERP analysis just can only capture what is phase locked across all trials, right? So if something is out of synchrony, then it gets cancelled out in the averaging, and we don't see it. When we do spectral analysis, it allows us to take a signal. So basically, what we do is we take each single trial, we transform the time domain signal to a frequency representation, and then basically we throw away the phase, right? This is what we can do, and then so we're only left with a representation. You know what? I'm going to go ahead and show this to you. Where is it? Hold on, I'm going to find the slide is not where I wanted it to be, so I'm going to find it. Oh, it's here. It's hidden. Okay. Okay, so sometimes in the EEG jargon we call ERP analysis of evoked responses, and then we have analysis of induced responses. It's sort of a bad name, but all this means is that induced responses are responses which are not dependent on a specific phase. So when we average these responses, we get this average, we get this phase-locked activity that has the same phase relation to the onset of whatever we defined our trial as. And if this kind of activity, which is not phase-locked, there's definitely a consistent response, but it doesn't have a specific, a consistent phase relation to this time point, this gets cancelled out. So when we do spectral analysis, we can take this oscillation and say, okay, there was an increase in 10 hertz power, for example, and we get, instead of this, we have a representation of the power of this frequency, which will look like this, right? And then like an envelope of this shape. And then when we average across these trials, we would see this spread out increase in power. Okay, so we haven't lost the information. Instead of saying that there is this phase-locked time domain response, we say that there is an increase in a certain frequency band. So we can also detect non-phase locked activity. Second reason is that many neural phenomena occur actually in very specific frequency ranges. You've probably heard of alpha, beta, gamma. It was probably in the paper that you read, and we're going to talk about this in a moment. There's also types of analyses that focus on specific phase relations. If we'll have time to talk about it at the end, but actually, no, I'm going to have an example of this pretty soon, so you'll see what I'm talking about. And another important property of spectral analysis is that it allows us to talk more about neural states. So, for example, and this is again going to be in the one of the examples, we can talk about like a certain spectral power, certain shape of the spectrum, which characterizes the state of a brain or a state of a certain brain area, and then we can compare it across time or across conditions or across subjects, etc. And this is something that we can't really do with ERP analysis, which is only concerned with a response to a specific event. Okay, so I can measure EEG and say, okay, right now there's this amount of power in the alpha frequency band, and then when the person closes their eyes, there's an increase, but it's not locked to a specific event. It's something that's continuous. Yeah. So we talked about this. All right. So I said that certain neural phenomena are characterized by activity in specific frequency bands. So these are the classic um, definitions of EEG frequency bands. And the important thing to realize about them is that on the one hand, they're not strict, they're definitely fuzzy. There's no real difference between, or hard separation between 7 and 8 hertz or 12 and 13 hertz. And especially in the high frequencies, in the beta, gamma, and high gamma, you would see different definitions in different papers. In my work, I don't really see any difference between gamma and high gamma. I see maybe different. So for me, gamma starts at around 50 hertz if I look at EEG, and 30 hertz if I look at intracranial EEG. And it depends if what you're looking at. So it's very, very fuzzy. Some people talk about high gamma and low gamma, high alpha and low alpha, above and below 10 hertz. For some people found a different behavior of these frequency bands. So that's one thing. But on the other hand, these are definitely not arbitrary. So it's not like somebody decided, okay, let's just chop up the frequency band into these categories and it's stuck. No, the brain really, really behaves in a way that it consistently looks like there's a reason for this separation. Okay, so for example, we're going to talk about the alpha rhythm, that is very, very consistently showing up around 10 hertz for any human. So yeah, so these distinctions are very, very useful when we analyze the EEG, because we can start with, okay, let's look at this frequency band, and there's a big chance that what we see in this frequency band would be different in a consistent way than if we looked at a different frequency band. So I'm going to go into two examples. I'm going to talk about what I think are the most popular frequency band for research, for EEG research, which is alpha and gamma. So let's start with the alpha rhythm. So the alpha rhythm is it's like how you can see that Chinese wall from space. It's the one neural phenomena that you can see with the naked eye when looking at EEG recording. When your subject is in the experiment room and you're just looking at whatever comes out, you can actually see alpha rhythm. Everything else that you can see with your eyes is just noise, it's muscle noise and stuff like that. But this is the neural phenomenon that you can see, and this is an example of what it looks like. So this is a 10 hertz oscillation, and this is something that Hans Berger already noticed in 29, when he invented the EEG. It's really affected by closing your eyes. So whenever you close your eyes, there's a really strong increase of these alpha oscillations, these 10 hertz oscillations. So this is the time representation. Here we can see a time frequency representation. And I'm going to stop for a moment just to make sure that we know what we're looking at. So here, so this is a very popular representation of changes in the spectrum over time. So here the x-axis is time, the y-axis is frequency, and the color is the power or amplitude. So what we're seeing here is that after closing the eyes, there's an increase, a continuous increase in a frequency band more or less around 10 hertz. Okay, so this is just a time frequency representation of this signal, and we're going to go into more detail about how we make those. So since there's been tons of studies about the alpha rhythm since the 1920s and to today. Right now, more or less the consensus about it is that the alpha rhythm is involved with or associated with sensory disengagement. So whenever I pay less attention to what is going to my sensory input and more attention to maybe more internal processes, I turn my attention inward, then there's an increase in alpha power. Again, the best way to see this is closing your eyes, which is a very good way to shut off external input. But also if I just change, my covert attention from attending, if I have to attend, if I have a task where I'm looking at a screen and at a certain time I need to really attend a visual stimulus, then you would see a decrease in alpha power. So it's a really strong index of sensory engagement. And one nice example study that I want to show as an example of research into the algorithm, I think it's my favorite study on this topic. It came out in 2011. And it was already known at this time and a long time before that, that, as I said, that algorithm is involved with attention. So the question of not this study, the studies that came before it was that does it have a causal role? So, for example, if I show you if I ask you to detect a stimulus that is hard to see, so you see it about 50% of the time, and if I record your EEG and see what your alpha power is at the time of the stimulus appearance, so it's not affected by, you're always paying attention, but of course alpha power fluctuates, and your attention probably fluctuates. So can this alpha power, does it have a causal role in your perception? In other words, will you have a harder time seeing the stimulus if your alpha power is high when it appears at the stimulus onset? And it was found that this is indeed the case. So there's a difference, and you can see this in the study here. So when your alpha power at the time of stimulus presentation is low, you would have a higher detection rate than when it is high. What this study showed that was new is that this also depends on the phase. So if you measure so when you do a time frequency decomposition, again, you get the amplitude information, but you also get the phase information. So if this is our alpha rhythm, and it's just an ongoing rhythm, it's not locked to any event, but then at some point we get this stimulus, and the stimulus can land here, for example, or it can land here at different phases of the alpha cycle. And what this study found, and other studies similar to it also found, was that this also makes a difference in the probability of detecting the stimulus. So, and this is what you see here. So different phases of the alpha cycle are associated with different detection rates. And this led to further hypotheses about the alpha rhythm also acting as sort of a post-inhibition mechanism. Yeah, I'm not going to go into the theoretical discussions about it, but I think this is a very cool finding about how the EEG can help us really find very high temporal resolution phenomena of attention, for example. And this is also an example of two things that I mentioned. One is talking about phase relations. So we're not really we don't really care about the amplitude or the shape of any evoked response. We have ongoing activity, but this ongoing activity, because it's oscillatory, it has a specific phase, and this phase can have functional significance. And the other idea is that this is not event related, but an ongoing state, which has, especially the alpha powers, and we can characterize it as an ongoing state of the brain, and we can link this state to cognitive states like attention, how much we are attending the stimulus, or how easy it is for an external stimulus to excite our visual cortex, for example. Okay, any questions about this study? All right. So this is just one example about research into alpha oscillations. And I'm going to talk a bit about the gamma range. So similarly to the alpha oscillations, there's also a phenomenon of gamma oscillations. When I say oscillations, I mean this kind of phenomena. We have this periodic increase and decrease of the local field potential. And this was found mostly in the visual cortex. So here, for example, we have a study where monkeys were presented with visual images, and the electrodes in their V1 found these oscillations about 80 or 70 hertz. And this is again a time frequency representation of that. And this is a spectral representation of this. And the important point here, or a point that I'd like to make here, is that showing this is important because, and this is something that we're going to talk about more all through this lesson, but it's very important to be clear when you're talking about spectral representation, whether when you talk about a specific frequency band, whether you're actually talking about oscillations or you're talking about different types of spectral phenomena. You know what? It's going to be better to talk about this later. I have a better slide for that. So, yeah, just forget about it for the moment. Okay, so we know there's this phenomenon of gamma oscillation, and I think the hottest take on the gamma oscillations so far is a theory that links them to dynamic functional connectivity between areas of the brain. So the idea is that in a similar way that to what I mentioned with the algorithms, which is that specific phases are associated with different excitability of the brain. So if it's easier, so in a sense, like the first in a specific phase of the alpha cycle, it's easier to see a subliminal stimulus. In a similar way, you could say that a neuron or a neural population can be more receptive to input, can be more easily excited when it's at a certain phase of local gamma oscillation. So it would be, it would have a lower sub-threshold membrane potential, and therefore it would be easier to excite and create an action potential. So the idea is that neural populations that are synchronized, that have the same phase of this fast gamma oscillation, would be functionally more connected in the sense that if this neuron fires at a certain time, when it's during its more excitable phase, okay, when it's more likely to fire, then another neuron, which is receiving input from it, would be more likely to also fire if it's on the same excitability modulation fluctuation. Right? Is that clear? And another neuron which is out of phase would be less likely to respond because it might be at the same time on its non-excitable phase. Okay, so this is the theory, and it was demonstrated pretty nicely in 2012 by the group of Pascal Fries when they recorded from the visual cortex of monkeys that had two stimuli that correspond to different receptive fields in V1. So if this is V1, then these are two receptive fields corresponding to two different stimuli. But these two receptive fields were associated with the same V4 receptive field. Okay, so the V4 receptive field is larger. It receives input from several V1 receptive fields. So both these stimuli activated V4. So what are we seeing here? Yeah. So okay. So I'm not showing this here. There's another figure showing that when you show only one stimulus, it would activate just one of the V1 areas, but both of them would activate V4. Okay, this is not what you're seeing here. What we're seeing here is an experimental conditions where both stimuli are present, but the monkey has to attend only one of them. Okay, they have a task, but they need to send only one of these to Gabor patches, I think it was. So what happens is that, of course, both of them activate V1 because they are both present, and both of them activate V4. But the difference is that when we measure phase coherence between each of these V1 areas to V4, and phase coherence is basically, there's different ways to measure it, but basically what we're asking is that whether there's a consistent phase relation between two signals. So whenever the phase of one signal is around the peak of the cycle, then the other signal will also be at the peak, etc., or otherwise there's no statistical relation. So the finding was that the V1 area that is attended, corresponding to the stimulus that is attended, has a higher phase coherence with a V4 area around this gamma frequency band, around like 70 hertz. All right. So what we're seeing is that in both areas, so if this is V1 1, this is V1 2, and this is V4. So there's this oscillation here, and there's this different oscillation, the different phase. And V4, and these both have the same power, okay, the same amplitude, because both stimuli are there. So these two areas are both activated, but V4 is more synchronized with only one of the V1 areas, depending on which one of them the monkey is attending. All right? So this is a very nice representation of this idea that two brain areas that should be more talking to each other more than two different brain areas are also more synchronized in the gamma frequency band. Questions about this? All right. Okay. So right now we talked about gamma oscillation, but I also said that you have to be careful when talking about oscillation because no, again, I'm going to keep this for later. But another very important phenomenon, maybe even more important phenomenon associated with the gamma band, doesn't have anything to do with oscillations. It has to do with broadband power. So basic broadband power is that if oscillations represent an increase in a very specific frequency, okay, so around 70 hertz in this case, broadband power is an overall increase in a wide range of frequencies, so maybe between 50 and 300 or whatever. And this is again a distinct phenomenon that can be measured in the EEG and the intracranial EEG, and it was found that this kind of signal is very strongly coupled to neural spiking. So in this study, for example, this study recorded intracranially from humans. They actually have a single unit recording from humans who were implanted with electrodes for the treatment of epilepsy. And so they recorded local firing rate, and they recorded the local field potential, and divided it into frequency bands, as you can see here, and and looked at the correlation between each frequency band and the firing rate, and they found a very, very, very strong correlation between broadband high-frequency power. So in this case, definitely from 100 and above, but I can say it's also true from around 30 or 50 hertz, and much less so for lower frequencies. So for example, the alpha band, you can even say it's, well, it's not, it depends how you look at it, but generally it's negatively correlated with firing rate, which makes sense if you remember that alpha band is associated with less attention to the stimulus. So it depends, of course, on the context. But for example, if you're looking at visual responses, then usually it would be stronger the lower the alpha band power is. And for example, the frequency band where we found the oscillations we talked about in the previous examples that are evoked by the stimulus. There is a correlation there, but it's much weaker than the correlation of the broadband power. The point I'm trying to make is that even though this is gamma and this is gamma, seeing these narrow band oscillations and seeing a global increase in power across a wide frequency band, even though they overlap in terms of frequency, these are really different neural phenomena. And the second one, the second phenomena, the broadband increase in power, is really closely correlated with spiking. So in many cases, especially in intracranial EEG studies, which don't have recording from single neurons, but rather record from about maybe a millimeter of cortex, this is really high frequency broadband power serves as a very strong index, very good index for local firing rate of this area in the brain. So this is another study showing a similar thing. So they again recorded from single neurons. Or is it the same study? No, it's a different study. And here they just show the proportion of the neurons that they recorded having a positive or negative correlation with each frequency band. For example, these lower frequencies, there's a low proportion of neurons having a positive correlation, and even more of them. So, for example, here in the in the lower frequencies, there's a higher proportion of neurons that are negatively correlated with the power in this frequency band, and the best correlation is found in with the broadband power. So just the global power between, in this case, it's between 2 and 150 hertz, I think. So it differs between studies, but and for example, for the gamma band, so I think this is like between 30 to 80 hertz. Again, there are many neurons that are positively correlated, but there's also a lot of neurons that are negatively correlated with this frequency band. So there's different overlapping phenomena here. What did I say about this now? Hold on. Yeah, okay. So, I'll talk a little bit about how we methodologically how we do spectral analysis. So this will be a bit more methodological and less theoretical, but it's going to get us right back into theoretical ideas pretty soon. So there's many different ways. Yeah. Saka? Okay, so let's take a break. Yeah, it's a good time for a break. Yeah. Okay. Welcome back. Yeah, I think I might even have enough time to talk about everything I wanted to. Right. So let's talk about how we do frequency decomposition. So basically, it all boils down to the Fourier transformation. But when we look at the EEG signals, then usually we also like to see how the spectrum changes over time, and there's different ways to do that. So the first one, which is the easiest to understand, is called the short time Fourier transform, and basically all this means is that you take a short window, you do a Fourier transform, you get the spectrum, and then you look at another window, you do a Fourier transform, and just look at how it changes over time. It's a little bit more complicated than that. Usually you'd have to multiply your signal by a certain window to smooth it, to avoid artifacts, but this is basically the idea of having a Fourier transform at every specific time point. So I think I want to say now that all of the methods that I mentioned, I think all of the possible methods for spectral decomposition are actually mathematically equivalent. They're on the theoretical level, you're doing exactly the same thing. But there are important practical differences between them, which I will explain. So I think the most popular method for looking at time frequency representation is called the wavelet transform, and I'll show you what it looks like. Basically, so we have a signal over time, and we want to create the kind of time frequency representations that I showed you before, having time on one axis and frequency on the other axis, and showing how power at different frequencies changes over time. So how the Fourier transform works, the wavelet transform is, it's based on a, so this is what we want to create. So it's based on this short function called a wavelet, and there's different types of them. I think every EEG study uses the same function. It's called a Morley wavelet. Basically, all it is a sine wave, a sine function multiplied by a Gaussian. So basically, it's just this shape. Okay, so we have the sine wave and the Gaussian. And basically, what you do is you decide which frequencies. You have to decide which frequencies you want to look at. So this will be your y-axis here, and you construct for each frequency this wavelet according to the frequency that you're, So this would be low frequency, and this would correspond to higher frequencies. And then basically you just convolve this wavelet with the signal, okay, with the signal up there. So for example, if this is my signal, then when I use the wavelet that corresponds to this frequency, so it would look like this, okay, more or less. Then when I convolve this function over this function, I would get a low value here, and a high value here, and a low value here again. Okay, and when I do the same with higher frequency, so this wavelet, okay, then I would probably get the same low value across the function. Now, if you're really paying attention, then you would say, well, this is not really true, because even when I use the the right frequency, I will get a high value here, but then when I change the phase, I will get a negative value, right? Because it's out of phase. So, and this is not what I want to see. I don't want to have my result showing, a really high power and then really low power and then really high power. This is not what I'm looking for. And this is because our wavelets are actually complex wavelets. So at each time point, we're convolving not with just this function, but also with its imaginary or sine and cosine equivalent, which is, I'm not going to draw, but it's just the same thing shifted, so cosine instead of sine. And then we take this and we actually convolve with this complex function, and we get a complex result. And this complex result will have a consistently, so I erased it, but when we move our complex wavelet across this oscillation, then of course for the sine and cosine wave, the result of the convolution would oscillate up and down, but if it's but the size of the vector of the complex vector would be fixed. Does that make sense? Again, it's very hand wavy. But basically, the idea is that since we use the complex representation, then if we take this signal, okay, which has a very clear oscillation. So when we use the frequency that corresponds to this frequency in the wavelet analysis, then when we convolve with a sine wave, we get 0 here and then this here, and when you convolve with the cosine, we get sort of something like this, like it's a 90 degree, not 180 degree change, and then the amplitude of the vector defined by these two, the real and imaginary component, would look like this. Okay? Make it clear. And this is the amplitude. This is the result of our wavelet transform, the amplitude of this frequency across time. Okay? And then, of course, we have also these. We get this when we throw away the phase component, but we can also use, of course, the phase component. For example, if we want to do an analysis of phase relations, then we can use the phase information in addition to the amplitude information. But this is basically how the wavelet transform works. Any question about that? I'm going to show you an example. So this is both example to understand how wavelet works, but also it also shows you how, more importantly, it shows you how different time domain signals look in their time frequency representation. So I made a signal here that's made up of 3 different types of signals. So there's a sharp spike here, there's a 10 hertz oscillation here, and here it's just noise, just random noise. So the middle one is clearest in the time frequency representation. When we do a wavelet transformation, we get this clear increase in narrow band power, okay, because there's power in 10 hertz, but there's much less power in 11, 12, and 13 hertz, for example. What's going on here is important to understand, and this is the part that I didn't want to mention before that I mentioned now. It's very easy. It's much easier than you would think for a lot of people to confuse the mathematical idea of spectral decomposition, meaning the idea that a function over time can be represented as a sum of sine functions. To take this idea and confuse it with a more physiological interpretation, which is that when we see an increase in a specific frequency band in our signal, this means that there is actually a neural source behaving like a sine wave, behaving like an oscillation. Okay, and the best, I think, example of showing how this is not true is these two examples of the spike and the random noise, because a spike is actually has in terms of a time frequency decomposition, you can see that it has power in a very wide band of frequencies. And why is that? There's different ways to explain it, but the way I like the best is going back to the demonstration that I did with constructing a square wave. So how would you construct this with sine waves? I mean, first it looks really hard because sine waves are continuous, so why would they all why would they result in a single spike? So basically, if you want to construct this this shape, what you would need so you start with the lowest frequency component. So something. Okay, I'm going to draw it here. Yeah. So this is your spike. So you'd start with your lowest component. Which is this, right? But you're not there yet, so maybe add, you need something that peaks here, but it's higher frequency, so maybe something like this. But you're not there yet, so maybe add something that's more high frequency, looks like this. I guess it's pretty hard to because you're not seeing it build over time, but eventually, so theoretically, if this is really a delta function, if it's really 0 and then 1 at a specific time point, what you would need is an infinite series of sine waves that are all they all peak at the same time. So here you have the sum of all the sine waves, so it would be infinite like a delta function. But then the farther you get, or actually theoretically just beyond this point, since you have infinite series of frequencies, and each one of them has a slightly different frequency, a series of sine waves, each one with a different frequency, then some of them would be out of phase, and so they would not sum together in the same way that they sum together here, and eventually you get this spike. Okay, so in more day-to-day examples, then this is not an infinite delta function, but basically the idea is that sharp transients are associated with transient wideband increasing power. Okay, this is a phenomenon. So this is what it looks like here. Okay. Something important I forgot to mention about the Wavelet transform. The important difference between the Wavelet transform and the short time Fourier transform, because again mathematically they're basically the same. But the idea of the Wavelet transform is that you have a different. So you could. I didn't mention it, but you could see it here that the wavelets have a different width, okay, or duration. And this is because what is kept constant is the number of cycles, okay, or the width of the Gaussian in terms of cycles. And this means that higher frequency you have shorter wavelet function. And this is desirable because there's another very fundamental point that need to be understood about time frequency representation, is that even though we have a value at each specific time point of this time frequency representation, there's really it's meaningless to talk about power of a specific frequency band in a specific time point, okay? Because frequency, by its definition, is something that evolves, that happens across a temporal window. Okay, there's no theoretical way to look at a window of 10 milliseconds and say there is a high 10 hertz power in this window. Okay, it doesn't make any sense because 10 hertz means a cyclic phenomenon that changes at a wavelength of 100 milliseconds. So it's not defined at 10 milliseconds. Okay, so it's very important to understand that whenever we have a time point giving a measurement of power at a specific frequency range, it actually refers to a temporal window around that time point. So because of this property, we can talk about when we talk about higher frequencies, we can talk about shorter temporal windows, and we can track the resolution of the fluctuations in power with higher resolution. So it makes sense to use shorter windows for higher frequencies. Okay, because if we need a few hundred milliseconds to talk about how alpha power changes, there's no reason to use this very low temporal resolution when we talk about gamma power. Okay, so the wavelet transform really allows you to do that by having basically different temporal resolution for different frequencies. Yeah.
Is it the case that typically a program like that, wavelength has a different resolution in different frequencies, or in the end you use one window per frequency?
So
The time resolution is what?
sorry.
So the time resolution of that spectrum changing in different lines?
For different frequencies, yes. So for example, so let's take this example of the spike. When you look at the temporal representation, you can see that it's 0 here, and then it becomes 1 or 10 here, and then it becomes 0 here. Okay, but when you look at the time frequency representation generated by wavelet analysis, it sort of looks like in the lower frequencies, it starts earlier than in the higher frequencies. Okay, of course it doesn't. Nothing starts earlier. This is what's happening in the signal. There's nothing happening here. Okay, but when you look at a time frequency representation, because of this property of each frequency having to have a different this time window, this extended window that it refers to, then you can say that when you look at 30 hertz, you can say that there's no 30 hertz power here, but there is 30 hertz power here. But you can't do the same with 5 hertz, okay, or 10 hertz. So this is why it looks like
So the window of interpretation is different.
yes, the window of interpretation is different. Exactly. And again, there's no way to go around this because we can't have this resolution for lower frequencies because it's not defined. Okay, it doesn't make any difference. We can equate the resolution across all frequencies, have the same resolution, and have this have it start the same as all frequencies. But then we'd have to go with the lowest frequencies that we want to look at and set our window according to that frequency. And this is basically the idea of the short time Fourier transform. It's the same window size, but then it really defines what is the lowest frequency that you can look at. Okay, and the example over here of the noise here is just to show you that noise is basically, so if it's just random noise, unfiltered random noise, it would have the same power across all frequencies, and this is what you see here. So across time, you have this broadband power across all frequencies, and this is sort of similar to what I showed you earlier with the high frequency broadband gamma power that's correlated with spiking rate. Okay, this is sort of what the signal looks like. It wouldn't go down to 10 hertz maybe, but it would be this very broadband and continuous signal. So my point from before was that, so for example, if we took this signal and we took this, and we really all we care about is oscillations, okay, like alpha oscillations, for example, and we took this narrow band view, which is narrow band and narrow-minded view of analysis, saying, okay, we just look at 10 hertz power. So we take our signal, we filter it around 10 hertz, and we see how the power changes over time. then what we would see is this increase in power, then decrease, then increase again, then increase here too. Okay, and it would look like, we could naively interpret this as saying, okay, so in the brain we have alpha oscillations here, then they go down here, and then they start here, and they go a little bit down here. Okay, but obviously this is not a good interpretation, right? Because this has nothing to do with oscillations, right? And to understand this, we have to look at of course at this, but usually signals from the brain are not as clear as this. But look at our entire time frequency representation and really be skeptical about what this tells us about the actual behavior of the signal in specific frequency bands. Yeah. So just to reiterate this point, and I'm really stressing it because it might, for some of you, it might sound trivial, but this actually has the entire a lot of the neuroscience community baffled. So it's important to stress again that having that high power in a specific frequency does not necessarily mean an oscillatory signal. It just means that when you take the time domain signal and construct it out of sine waves, then you also have to use sine waves from this frequency. Okay, but it's a mathematical construction. It's not the same as really discovering that the underlying signal, that there is a specific neural source in the brain that contributes this sine wave to the signal that we measure eventually. Yeah.
Before we talked about causality, by causing alpha stuff in the brain by TMS, we cause somebody to perceive death or more.
Yes, in the example I showed you, it didn't use TMS. It was just measuring the ongoing endogenous alpha oscillation.
I think that was written was supposed to read. There was an experiment that they caused by TMS alpha frequencies to be the power to be higher or lower, and then they say that this causes the perception to be lower or higher.
Yeah.
But from what you are saying now and from what I told before, that these oscillations, the power of the alpha frequencies are not something that's like responsible for the perception. It's something that comes as a result of the very messy activity in the brain that causes these oscillations. So how can they talk about causality between causing these power frequencies and the perception?
Okay, there's two different things here. One of them is the second one would be about causality. The first one is about interpreting something as an oscillation, which is what I was talking about now. Oscillations and non-oscillations, it's not really there's no clear line between what is an oscillation and what isn't. Okay, but there are some things that you could say, okay, yeah, this is an oscillation, and alpha rhythm is one of them. So the alpha rhythm, it's not. So one thing is that the first thing is that when you record EEG, you can actually see this sinusoidal behavior of the local field potential, which is narrow band, and which is, it looks like an oscillation, so it's an oscillation. There's no proof. I mean, there is. You could say that maybe this oscillation is not really. There's no source in the actual source in the brain that behaves this way. It's just a coincidence in how different. It's like maybe it is like a series of delta functions that behave like each area of the brain has this spike, and somehow they correlate in the way that in the EEG signal it looks. But it's a far-fetched interpretation, right? I mean, plus you can also see this alpha oscillation when you measure in higher spatial resolution with intracranial EEG, with depth electrodes. So specifically the alpha rhythm is definitely an oscillatory phenomenon generated by neuropopulation. So on the other hand, when you're measuring gamma power on the scalp, and we're going to get into this also, then it really becomes much more messy thing. Saying, does this reflect oscillation? Maybe it's different. It looks wideband because there's different oscillations and they're all added together, so it looks more broadband than narrow band. Or is it just maybe broadband noise that is somehow filtered and then to look more narrowband, even though it's not oscillatory. So there's all these questions which are kind of hard to answer. But in some cases, it's easier. So the two examples that I showed you of the alpha and gamma oscillations, these are pretty clear-cut examples of truly oscillatory phenomena. The second point that you're making about causality, in the study that I showed you, I said causality, but I said something about causality, but it was wrong because this study doesn't prove causality in the sense that it doesn't show that the alpha oscillation itself causes the difference in performance in the attention task, because it could be that it's just an epiphenomena of a different factor, like attention causes fluctuations in attention cause a difference in behavioral performance, and they also cause somehow the alpha power to change, but the alpha power is just epiphenomenal. So that study only showed a correlation.
Even in
But
the paper, each time they presented a different frequency, they said that this facilitates, or this is responsible for some kind of perception.
yes, so once you introduce TMS into this story,
Not necessarily with the
oh,
TMS. That's
so
what surprised me in the paper. That each time they presented like in different frequencies, they say that this facilitates synchrony between.
did they present the stimuli with different frequencies?
I don't really remember.
So
Just this causality. That in the TMS, you can talk maybe about causality because you're causing this
Yeah.
power and okay.
Yeah.
But in different papers, they always talk about. In this paper, sorry, they present different frequencies, and they say. Wait, I'll give you just an example. Sorry.
wait, I have until
Yeah,
quarter to
maybe
4.
we should
Yeah, then
talk
I don't think we have time for
about
this. We have to move on.
Okay.
Yeah. So I mean, I can answer maybe after the class. Okay. Okay, let's move on. Just one small point about wavelet transform. Besides picking the frequencies, there is one parameter that you need to choose, which is, so I said what is kept constant is the number of cycles for each wavelet, but you have to choose this number of cycles. So there's something called the wavelet constant, which determines how wide or narrow these wavelets would be. And the difference that it makes is that choosing a different constant would create a different representation. It would be just as valid, but you have this trade-off between temporal and frequency resolution. So the higher your wavelet constant is, meaning the longer your windows are, you would get better frequency resolution, because when you're convolving longer signals with each other, you're more sensitive to to how precise the frequency is. But of course, since the window is longer, you're decreasing your your temporal resolution. So these are two representations of time frequency representation of the same signal. But here the wavelet constant is lower, meaning we have better temporal resolution. So you can see the spike here is sharper, okay? But we lost some of the frequency resolution, which is easy to see here, okay? So these are, again, this is the same signal, and it just demonstrates. It's not. You could say maybe, okay, so maybe I could use this high wavelet constant to get the frequency estimation, and then the lower one to get the time estimation. But this is not really true, because all of these are true in the same way. It's just you're asking a different question. Okay, you're asking questions about longer or shorter time scales. All right. The second method that I'll mention, which is my favorite one, it's called the Hilbert transform. Again, mathematically equivalent, but what you're doing here, what is practically different, is that so in this case, in the wavelet transform, basically you're always filtering. In all of these methods, you're filtering your signal at different frequencies and then looking at the power of the filtered signal. But here the filtering is is done implicitly in the convolution, in the Hilbert transform, you take charge of the filtering, and then you apply the transform. So, for example, I have this signal here, which has these low frequencies and then these high frequencies here, and I want to look at high frequency power. So, basically, in a Hilbert transform, I decide what is the frequency band that I'm looking at. So, for example, here I would filter. So, in this case, for example, I just do a 30 hertz high pass filter because I want to look at broadband power in the 30 and above hertz and above band. So first I filter, and I get this green signal, and then when I apply the Hilbert transform and again I would get a complex result. So I have to take an absolute value of the result, and this is what I get. I get the envelope of the signal, and then of course I can square it to get the power. And I like this. This is useful if you want to talk about a specific frequency band. Wavelets are very useful for visualization because you get this very nice picture of power across frequencies. But if I want to say I want to look at fluctuations of alpha power, then it's easier to first filter around 10 hertz in exactly the way that I want to, and then look at power over there. Yeah, and there's other methods. I'm not going to get into them. I know them less well, but again, in essence, they do the same thing. All right, very quickly, I want to talk about how much time do I have? 15. Okay, so I want to talk about artifacts, but we're going to be revisiting some of the same ideas in this part as well. Okay, so what are artifacts in EEG? There's maybe three major categories. The first one would be electrical noise. So this would come from here in Israel we have a 60 hertz AC alternating current frequency, and this would show up as a very clear spectral peak at 60 hertz in your EEG recordings. Plus any other electrical equipment around you would also introduce radio frequency noise. I had one case where I had this mysterious 70 hertz, very narrow band 70 hertz power in my signal that I couldn't understand where it came from. Eventually, I realized that it would happen in only like a subgroup of my subjects, and eventually I understood that in this specific subgroup, I forgot to change the screen refresh rate from 70 to 100 hertz, or somebody changed it to 70 for some reason, and this showed up as a 70 hertz oscillation in my EEG recording. I didn't see the 100 because the 100 was already filtered out anyway as a harmony of the 50 hertz line noise. So I said 60 hertz, yeah, it's 50 hertz in Israel, of the 50 hertz line noise. So anyway, I didn't see the 100 hertz, but when it was 70, then it showed up as an artifact, which took a few days to realize what happened. So that's one category. A second category is biological noise. So this is mostly muscle noise. So I think I showed you maybe in the first lesson how sensitive EEG is to muscle. So of course, if you do something like move your nose or squint or really use your muscles of the face, it completely screws up the signal, and you have to throw away this segment. But of course, your muscles are always working, so that also introduces noise. And then there's eye movements. Specifically, I'll show you later about the eye movements. Heartbeat also sometimes you can see. And the third category is less well defined, but sometimes you can think about also neural sources of artifacts. For example, some people like to filter out or to treat the alpha band as noise. Sometimes they want to look at the ERPs, and then you have this alpha rhythm which really overlaps with the frequency range of most ERPs around 10 hertz. So sometimes you want to filter that out, but that's kind of problematic. But yeah, you can think about it as an artifact. The way artifacts are handled is basically falls into two different categories: discard or reduce. And there's different strategies for different kinds of artifacts. Discarding means just saying, okay, this temporal epoch is hopeless. I'm going to throw it away. So this is usually done in a way that you take your EEG recording and you apply some kind of either automatic threshold of just amplitude or some kind of other criteria of finding artifacts. And whenever you have an artifact falling within a trial, you throw away the trial. You always have to do that because some trials are always going to have very, very loud noise, like if the subject moved his nose or something. Sorry. So this is pretty simple. A more complex idea is trying to get rid of artifacts without getting rid of the data, so reducing the artifacts. The simplest way to do that is, for example, when you can easily separate out the artifacts. For example, there's a very clear artifact of having your EEG signal drift over time. Okay, so if when you measure EEG across your time, like half an hour of experiment, the signal would start here and it would slowly drift very, very slowly to a different potential over time. Because the potential itself, the absolute potential is sort of arbitrary. So you get this drift, which has nothing to do with the brain activity, which happens on a much quicker scale. And then basically this is just a very slow frequency component, so you can just very easily get rid of it by filtering out low frequencies. So you do a high pass filter, maybe 1 hertz, maybe 0.1 hertz, depends on what you're interested in, and you get rid of this artifact. Same thing with very high frequencies. So if I'm interested in only in ERPs, which are generally slow, I can generally apply like a 30 hertz low pass filter and get rid of everything that is higher frequencies than that. So these are simple cases. A more interesting case would be dividing or decomposing the signal into different components and getting rid of some components, and I'm going to talk about this in a second. But generally, questions that you need to ask yourself when you're doing artifact correction. One question is this artifact meaningful only in the sense that it introduces noise to my signal, or is it an artifact also in the sense that it's an actual event that does not need to be included in my data? And an example of that would be a blink that happens when your stimulus is presented. So blinks, for example, are very clear artifacts in the signal, in that whenever you blink, your EEG signal goes like this, because when the eyelid covers your eyeball, it short circuits the voltage difference between your retina and your cornea, and you see it on the skull with a very, very large fluctuation, which you have to get rid of. But even if you get rid of this entirely, then in terms of the quality of the signal, then you still want to throw away trials where the subject, if it was a visual experiment and the subject blinked exactly when the stimulus is presented, then of course you don't want to use this trial, right? So you throw away this trial, but for a different reason, because of the significance of the event. So that's one question that you need to ask yourself. And another question is whether the artifact is systematic. So for example, if you see that the subject blinks systematically a very specific latency after the stimulus is presented, then of course, even though I have a very good way, which I will present shortly, of getting rid of the effect of the stimulus on my of this artifact on my signal, because it is systematic, it's enough for a very small residual of the artifact to remain to have a very clear effect on my ERP, right? Because if it happens at the same time, then even if I reduce it by 95%, there's still a very significant component left because it's synchronized. So in this case, if you have any reason to suspect that the artifact is systematic, then of course you still do your best to reduce it, but you also have to explicitly control for it. So in this case, I would say I would reduce the artifact, but it would also show that explaining my effect through the effect of blinks does not explain my effect, because something. Okay, I have to do like a control analysis. Is this clear? Should be pretty clear. Okay. Yeah. Okay. So let's see. 5 minutes. Okay. So I'm going to skip a little bit. What am I skipping? Yeah, I have to decide which is more important. Okay, I'm going to give you the story. No, I'm going to talk about ICA. No, I'm going to give you a story. Okay. Story is more interesting than ICA. ICA is more, you can learn about it somewhere else. So you remember the example I gave you with gamma oscillations and the idea or the theory that different brain areas communicate through coherence in the gamma frequency band. So this is a very interesting theory, and there was a lot of work trying to find or sort of work, not exactly this idea, but ideas inspired from this, which try to find evidence for gamma activity or gamma oscillations on the with EEG, because EEG is, it's much more accessible. So you want to see if you can find this phenomena using this tool as well. And so, for example, this study from 1996 found that if you show these kind of stimuli that produce an illusory contour, these stimuli are associated with an increase in gamma frequency band compared to similar stimuli that don't elicit this contour. And this was very interesting, and it was theorized that this has something to do with the relation between gamma oscillations and binding of features, of object features. A different study found that you have this increase in gamma power for recognizable objects versus stimuli that are just phase scrambled versions of the same stimuli but are not recognizable. And there were a lot of these studies, and moving forward to 2008, there was a study by a former member of our lab, Shlomit Yuval Greenberg, who's now in Tel Aviv University, that wanted to ask a question, taking this theoretical framework. She wanted to ask whether this increase in gamma power was related to the coherence of the stimulus or to the recognition or the identifiability of the stimulus. And so she had this kind of design. Doesn't really matter what the experiment or the results were. But she did find this increase in gamma power. And something went very wrong when she presented this in the Ein Gedi conference, like 2007, something like that. And who can tell me what that could have been? So again, this whole on the theoretical level. The theoretical discussions talk about how gamma oscillations are related to cognitive phenomena like binding or recognition or whatever. And this is the kind of time frequency representation that we're looking at. So what's wrong with this picture? Can you remember okay, let's go back. Here. So what kind of signal did that time frequency representation most resemble?
The wavelength constant, they're different.
Out of these three options, for example.
The first one.
Yeah, the first one, right? Because it was short in time and wide in frequency, right? So that's a very clear hint that you're not looking at something that came from oscillation, because oscillations, by their definition, are relatively narrow band. You have to be narrow band to be oscillations. If it's wide band, then you have all these different frequencies summing together, which really cancels out any clear oscillation. So oscillations are narrow band, and they have to have some kind of duration, right? If it's just one cycle, then it's not an oscillation. And here you have something which is very short in time and broad in frequency, frequency. which is a clear signature of a spike. So what really happened here? So whenever we move our eyes, we activate the small muscles that move the eye, and this small activation, the neuron that controls the muscle, generates this small spike. Okay, it's a very small spike that you can measure around the eyes. So if this is the eye tracking data, where you can see the eyes move, and this is the 3200 Hz filtered EEG from around the eyes, and this is the time frequency representation of this signal. Okay, so what is happening is that so these spikes introduce this kind of broadband frequency increase, and the problem is that whenever a stimulus is presented, there is a typical response of a inhibition and then rebound of saccade rate, of the rate at which we move our eyes. This means that whenever the stimulus is presented, there is a higher probability of saccades around a specific latency, around 250 milliseconds after the stimulus is presented. And these, because this happens in a specific latency, even though these are very, very small spikes, they can be recorded even as far back as the back of the head. And when you do a time frequency decomposition of each signal trial and then average across all trials, this is what you get. And this is an example of this really wraps together the two subjects here, because this is a clear example of biological noise, right? Noise from muscles of the eyes, but it was also deceived the entire human neuroscience community for more than a decade. Okay, there was more than a decade of these kind of studies that looked at this kind of signal and interpreted the brain from this signal from the eyes, because people are not good at interpreting time frequency representation. This came out in 2008 in our lab, and one good thing that came out of it is that we found that if we take this into account and use a tool called ICA, which unfortunately I didn't have the time to talk about, to remove or attenuate the influence of this artifact, then we do actually see high frequency gamma activity on the scalp. This is from one of my studies. And in this case, it's not oscillations, but it's broadband power from early visual cortex that can be recorded on the scalp. So, that's it.
Can you to associate that broadband with the gamma frequency?
So this is from 50 hertz and up. So this would be, I would call this. I wouldn't really use. I use high frequency broadband power. Don't even call it gamma.
Before the time.
So this was called gamma. This was called the induced gamma band response.
Even though it's like on all of the frequencies.
Yeah, I mean it is in the. It's not all. It starts at around 30 hertz. You see, but it is very wide band. Yeah, it is in the gamma band range. Yeah. Thank you.
כשאנחנו מדברים על הפאוור, שאלה ראשונה יש לנו את הפאוור, הנכון של האוסקילטור, והוא תוצאה של הניתוח שלנו. כן, שיש איזשהו חוקתיות או אחריות לזה, אבל עדיין הכוח של הפרקות היא תוצאה של ניתוח שלנו של פעילות שהיא מכל המוח. איך כאילו להפעיל כאילו אקטיבית ולשנות.
כן, זה מבחינה תיאורטית, ניקח למשל את הרעיון של הפרודקטיביטי בעיתונים. יש לך תופעה של מוגבלות יש לך נוירונים שיש להם אקטילציה בניברן פוטנציאל שלהם. ואז בהתאם לאקטילציה הזאת זה פשוט דרך לתאר את זה שיש תופעה מחזורית שאם מקבלים קלט בזמן שהאזור הזה נמצא בסיבוב גבוה, בזמן הזה שזה חזק.
מתקשר לשאלה בשיעור הראשון שלמדנו לגבי כאילו יש להם משמעות של איזו נכון? מסקנות מכאן ומסקנות של ההפך. אנחנו כאילו כמו שהם מוקפים את הבעיה הזאת, כאילו הם נותנים סיבתיות לפונקציה רק ספציפית על ידי משהו שהוא תוצאה של ניתוח של נתונים שלהם. זה מה שהתחלתי לחשוב, כאילו מה ההבדל בין מחקרים כאלה למחקרים שהולכים ברצפטור אחד מכל המוח ובאמת אחראי לקרוב. מסתכלים על זה לא יודע, הפעם ראשונה שמישהו משייך כך סיבה חזקה לגל של EEG
הגל של ה-EEG זה שלא נמצאים סיבתיות לצורה שנמדדת ב-EEG, נמצאים סיבתיות לתופעה שהזה החותמת האלקטרומגנטית שלה. זאת אומרת, אם יש לך נוירון שיש לו את הסאב-ספיישל אוסקיליישן, אז מה שסיבתי זה הממד, לצורך העניין, אני לא יודע אם ממש פילוסופי, מה שסיבתי במה שמעניין אותנו זה הממד פוטנציאל בכל רגע ורגע, אבל השינויים האלה גם מתבטאים בצורה האלקטרומגנטית שהנוירון הזה מייצר, ובתור אנחנו מודדים. אבל אם הוא לא היה מייצר, אם הוא היה שהוא שירדד והוא לא היה מייצר את השינויים האלקטרומגנטית, התופעה הייתה עדיין תופעה. זה לא מה שמדדנו שיש לו את הדבר הזה.
סיבתי במובן שזה לא מקרה, או לא משהו שגורם לדברים האלה, זה חלק מהמנגנון.
It's in Tel Aviv, first of all. Second, I don't think I really want to be doing further. I want to go back to just research. I want to do something different. Oh, yay! Okay, I got one, yeah. Laura?
Appointment to Barcode Drop.
Laura Pizza and Pizza. I will send you the list. It's growing, it's growing. What? No, just in general, good food and do you have some recommendations?
אני מקווה שהם ישמעו אליי. לא בלשבת בעצם.
Okay, try that one. Do you have time for this? I think I found it. Yeah. But
At
9 o'clock, it's so much better. And you went to it was the best of you.
there was a line.
Long line, really cute.
האמת שסוף השנה
There was a line.
פרויקט שהוא נגיד בשיטה של דבר נגיד מזיקו
But it was right across from the ship.
מה
And
נקודות
there was a line.
או שאפשר גם לעשות חזון שלך אולי גם
I almost took a picture and sent it to you, but I
נוכל להסתכל רשימת דברים
How it go? Oh, there's like burger places in the shop, like fish and chips. There's like no places. Fish and chips. The Latin place in the shop.
What Latin place? Because it's a sandwich place.
Oh.
I don't
Do
like
they have any
sandwiches.
Mexican food?
Yeah, so we have
Really?
Mexican
I don't know.
kind of lobster sushi that costs like €3 or something.
Yeah.
But if
Yeah.
you're downstairs, it's not a dinner.
Yeah, I know.
You're going to the restaurant.
Did you find any good Mexican food here?
I don't know.
It does not. It does not look like Mexican
There's
food.
a good Mexican food place in Tel Aviv. In Shuk,
Really?
surprisingly. I mean, there's one other good one that's
Go
not.
to yeah, there's good burger places.
This taqueria that's not in the Shuk, but there's another actually good, like it's actual Mexican people
There's a
there.
Jocknoon bar.
Jocknoon? Oh, I like
There's a
Jocknoon.
Jocknoon bar.
Jocknoon bar? But they
Yeah,
just
no,
serve
Jocknoon.
Jocknoon
Yeah.
and beer or something?
No.
Okay, I like that.
In the Shuk.
Jocknoon.
In
Oh, it's
Jocknoon.
in the,
In the Shuk.
okay.
Um,
Basically just walk through the Shuk and eat all of the things, is
exactly.
A few weeks
what
ago,
I'm hearing.
a few
I like pasta basta.
Pasta basta.
Classic, delicious,
Pasta though.
can't go wrong. Yeah, but it's fresh pasta, good sauces, sometimes that's what you need.
Yeah, sure. But it's just
Cheap.
40 shekels for pasta.
No, it's,
How much is that?
I mean, depends on what you get. If you get like a lot of toppings, then yeah, it could be
How much is like a pasta then? I don't know.
30 shekels.
Oh. Yeah, you need like a real meal for 30 shekels.
a few weeks ago went
It's a real deal.
to Shuk and so they sell the testicles.
Yeah.
Testicle?
Yeah.
Who is selling testicles?
In Shuk, and so there's a restaurant.
Are you sure?
Yeah, yeah.
Ew.
Where?
Ew.
I don't know. But anyway, it's in the Shuk.
I've never had any testicles.
Yeah. What do they call it? Rocky Mountain meatballs or something? Rocky Mountain something?
Have you had one?
No. I would never eat that. I'm pretty adventurous with my eating, but no thanks.
Not there yet.
No.
I've had kidneys. I had like the bait like
I don't like organs. I just don't like it.
liver's
I
so
don't
good.
like liver. I don't like it.
Mm.
I have tried it, but I don't like it.
Yeah, I don't like the kidney. I don't know. I like the liver a lot.
The liver is good.
Not my thing.
Tongue is so good.
I've also
Yeah.
had tongue and I don't
I
like it
love
either.
tongue.
I won't eat anything that can lick me back.
Tongue is the best.
The tongue, kidney.
Mm.
Oh, I was gonna tell you, on my way to Australia, I'm stopping in two places in China.
Okay.
Not for a long time, but I was wondering, I'm stopping in Beijing for like 12 hours.
Okay.
Is it worth it for me to leave the airport, or it's far from the city?
I don't know. I've never been to Beijing.
Come on. And the
12
other,
hours. I don't think.
So
I'm not sure.
you should do something.
It depends on the security check. Sometimes the security check will.
really.
You might have to get a visa, but it's still worth it.
Oh